Okay, so I believe we are live now. Can everyone see my screen and hear me properly? Please type 1 if you can see the screen and hear me properly. 0 otherwise. Fantastic. Thank you. You are my tester. Thank you. So let me just increase my thing. Okay. So welcome to our quantum webinar series. Apologies, my video, my camera somehow is not working, so you cannot see me. I will try to troubleshoot it before the Q&A. So I'm Bamborde. I'm your host, co-founder at Zyku. Just for the interest of time, I will skip the company intro and myself. You can connect with me on Twitter, LinkedIn, if you want to find out more about myself and about the company. I also have a special friend, Nisk the cat. My neighbors, Alice and Bob, asking me to look after Nisk while they are on well-deserved holiday break. Leaving the joke aside, it's a great privilege to host Dr. Nicholas Chancellor today. Nick is a innovation UK Innovation Fellow at Durham University, and he will be giving a talk on a recent paper that he and his co-authors published recently called Continuous Time Quantum Computing Beyond Adiabatic, Quantum Works and Fast Quenches. Nick specializes in continuous time quantum computing, particularly quantum annealing and hybrid quantum classical algorithms using continuous time hardware. Research-wise, in terms of the impact, Nick, interestingly, he helped pioneer the reverse annealing technique, which is currently available on the commercial quantum annealers produced by the D-Wave Inc. system. You can check the paper entitled Modernizing Quantum Annealing Using Local Searches. Interestingly also, he wrote one of, if not the first papers showing the use of quantum annealers for thermal sampling. So it's really great to have Nick with us, and I hope you enjoyed the webinar with him. Before I hand over to Nick, I will just share the session format with you. So there will be a main session with Nick, then we'll have like a Q&A and then the closing remarks. You can ask the questions on the fly. Nick was kind to say he's happy to answer if you have any questions, but ideally it would be great if you just ask it on the Q&A so he can address it at the end. That way it's not disrupting his presentation flow. Yeah, so you can follow us on social media. Please follow us on podcast if you want to be notified for our next webinar. And this webinar will also be available on YouTube. You can search us. For that, actually, we need your help to get to 100 subscribers so we can get a custom URL. So if you are on YouTube, please follow us. And you can also follow us on LinkedIn. So that's it from my side. I will stop sharing and hand over to Nick. Thank you so much. Nick?
All right. Well,
sharing, and the floor is yours.
First off, many thanks for having me. I'm excited to be here. So yeah, let me just start sharing so I can actually show my talk. Just get this on. View presentation. Okay. All right. So can everyone see the slides now?
Yeah, we can see.
Yeah. Oh, okay. I've just realized that I actually might not be able to see if anyone posts a comment or post a question during the talk. So
yeah, I'll check that for you. No worries.
Yeah. In principle, I'm happy to answer questions during the talk, but if I don't know about them, I might have to wait to answer till the end. Anyway, so this paper or this talk will mostly, especially the first part, mostly be based on a recent archive paper, giving some of the background on it on a previous paper we wrote as well. Later on, I'll sort of talk about a little bit of the broader context of some other work we've done. I suspect the talk itself will probably take roughly about an hour, but we'll see how long that actually ends up taking. And yeah, with that being said, I'll start. So, before anything else, a brief note about the terminology I use. For the purposes of this talk, when I'm talking about adiabatic quantum computing, I really mean where you're actually trying to be in the adiabatic limit, where you're really trying to be adiabatically slow. When I say quantum annealing, then I mean for one reason or another, you're away from the adiabatic limit. Either because you're in an open system and there's noise, or you're doing evolution that's faster than adiabatic. If you don't know quite what these words mean, I'll explain a little bit later on. But the reason I'm highlighting this right at the beginning is different groups use these terms differently. So just so we're on the same page about the terms I'm using. So with that having out of the way, let's first talk about the traditional picture of adiabatic quantum computing. So the idea here is you map a hard optimization problem, an NP hard optimization problem, to a Hamiltonian, and the solution's an unknown ground state. You slowly change from a driver Hamiltonian with an easily prepared ground state to a problem Hamiltonian. This could be, for instance, a transverse field, so basically a magnetic field pointing transverse to the way you've defined, say, an Ising spin glass type problem. And by the adiabatic theorem of quantum mechanics, you can get arbitrarily close to 100% success probability by running long enough, assuming you don't have any true crossings of energy levels, which you don't in models like transverse field Ising model. So this picture has some advantages and some disadvantages. The advantage is it's theoretically satisfying. The algorithm is effectively deterministic. If you wait long enough, it more or less, you can think of it always succeeding. You can always, 99.9, 99.99. In theory, you can always make your success probability arbitrarily high by just doing a single run that's longer. And it has a nice intuitive picture involving only the ground and first excited state. This is also nice because for certain kind of symmetric problems where you only have a single avoided crossing and you can figure out what the structure is, you can actually do a lot of mathematics around that. So it's nice for theory. It really, really is. However, let's for a moment, well, more than for a moment, let's assume that P not equal NP. In other words, this is basically saying hard optimization problems exist. And this is what most experts believe is true. So we'll assume it. But strictly speaking, it's not proven. And if we do this, basically what P not equals NP is that for NP hard problems, the hardest sort of class of optimization problems, your runtime will have to be exponential no matter what method you're using. And so if your algorithm succeeds roughly 100% of the time, then your total runtime needs to be exponential in the size of the problem. And the system needs to, if you're doing a closed system protocol, your system needs to remain coherent for an exponentially long time, that means. So as you add more qubits, the time which you need to maintain coherence grows exponentially. So practically, that's kind of a pain. What can be done about this? Well, if you just had really, really good hardware, nothing needs to be done about this, but realistically, there's always noise and things. So you could either restore coherence somehow, which is difficult to do in continuous time. Progress is being made on it. It's not what I'm talking about here. Dissipation can also restore coherence in some ways, but generally you'd need a very low temperature. So the point is, while maybe theoretically you could do this, it's very hard work. That's why I've put a wrench down here. On the other hand, what you could do is say, well, what if we ran much faster and succeeded actually with a low probability each time, an exponentially small probability, and just ran it exponentially many times. So we're still okay with P not equaling MP because our total runtime's still exponential. But we don't need to maintain coherence for this growing amount of time. We can maintain coherence for a mildly scaling amount of time. So this is conceptually kind of unsatisfying because it feels like playing the lottery, honestly. I put a lottery ticket here, and it's much less demanding for coherence. And I'd argue that other than the fact that it's also harder to do pen and paper theory in this limit, the real disadvantage it has is just that it's conceptually unsatisfying. Is it sort of psychologically the idea of running something with a very low success probability many, many times just doesn't sound very nice. Preliminary results actually show that it works quite well. But that's kind of what's going on here and what a big part of the message in the first part of this talk will be. So let's think of an example and actually look at a numerical example. And what I'm going to think about is a continuous time quantum walk on a spin glass. So what I have here is I've designed a Hamiltonian so that it's basically a transverse field Ising model. If you're familiar with that. If you're not, basically you have superposition of sigma x terms, which you can think of as bit flips effectively. This minus sign just makes the bookkeeping nicer. It makes it so your ground state is an equal superposition of everything with positive phase rather than alternating phase. And then you have a problem which looks like this kind of esoteric thing with sigma z's. Actually, this can be proven that you can map any NP hard optimization problem to this form, what's called an Ising spin glass. Since we're really more interested in the physics here than showing you can solve actual problems, we're just going to draw these from a Gaussian distribution and have what's called the Sherrington-Kirkpatrick spin glass. This is an older paper that we've now published in New Journal of Physics. Measure after a random short period and repeat many times. You can see what happens if you look at the probability of successfully finding your correct solution. It sort of oscillates. But if you look very carefully at the left side of the plot, it starts much lower than the average of the plot is. So something's going on to enhance your success probability, and we actually understand what that is. That's part of what the paper was about. But it would be great if you could land right on one of these peaks, but realistically, you have some difficult optimization problem and you have really complicated dynamics, and figuring out where one of these is, here we have two different examples. Figuring out where one of these is, you see they're in different places in the different examples, you're probably not going to do that. So what we do is we say, okay, let's pretend you measure at a random time, and then your average success probability is just the average of this, which if you squint very carefully is actually much more than where these start over on the very left side. So I called this a quantum walk. What do I mean by that? How is it a walk? So basically, what you can imagine is you can imagine the bit flips as walking you along a high-dimensional hypercube where you put all the bit strings at the corners of this high-dimensional hypercube. It's hard to visualize beyond 3 dimensions, But here's a sort of 3-dimensional or 3-qubit example, where basically these arrows are hopping along edges. And you can think of this as walking in this very huge high-dimensional space. It's a quantum walk, so you have effects like phase interference. And basically what the problem Hamiltonian does is it gives you phases on each solution which relate to the quality of that solution. So you can plot what the probability is of finding the correct answer, sort of on average, versus time. This is a sort of long time average. Well, on average, and you can see that's this gray line. It sort of jumps around like I showed before. The question is, why is this go higher? Here you can see that this probability of success starts out really low on the left. What you can do is if you plot out the energy expectations of the different parts of the Hamiltonian, of the problem, and what I've called the hop or H walk, they're the same thing. I probably shouldn't have used, or no, sorry, H walk's the total thing, so that the energy is conserved overall. If you just rearrange some terms a bit and realize that the total energy is just a linear sum of these two other terms, you can see that the difference in the expectation of the problem Hamiltonian is equal to the difference in the expectation of the hopping Hamiltonian. We started in the ground state of the hopping Hamiltonian, so this can only go up, which means this difference can only also has to go up. You notice there's sort of an overall minus sign difference here. So the expectation with respect to the problem goes down. So on average, you're finding better solutions with a higher probability. And the cost is basically that you your expectation for the hopping Hamiltonian goes up. And so basically you have this sort of energy conservation mechanism. This will come back later when we talk about when we don't leave this Hamiltonian just fixed and change it over time, which is what our new paper is about. So before we get on to that, let's talk a little bit more about this paper. One thing you've noticed here is there's a question of how much hopping do we do? How much do we hop because of this Hamiltonian? Basically, how strong do we make it? How strong do we make the moving across the edges of this hypercube versus the phase you get at each vertex? And does it need to be chosen very carefully? If you're familiar with, say, unstructured Grover-like search, you'd know in that case it does need to be chosen very carefully. Turns out for these spin glasses, I'm not going to go through the whole story here because there's a lot of details, but what we found is no, you don't need to be very precise, and it doesn't scale with size. You can see the paper with some details on that and what the heuristic are, but here's just some plots of what the P infinity, just long time success probability is versus this gamma, how strong you make the hopping. And this is important because if you were thinking of this as a real algorithm, if it could solve the problem very well, but you had to choose a parameter very carefully that was very difficult to choose, it would actually not be useful in practice. But that doesn't seem to be the case. So then we can continue with this quantum walk. We can numerically extract scaling. And we can just do the small sizes we can exactly simulate. And so these are numerical results. And basically, we can look at the scaling of the success probability. Success probability basically can be thought of as inverse runtime of the algorithm, because if your probability is sort of 1 over x, you can run it x times and reach a decent probability of success. And then a decent probability of success repeated a few times can become a very good probability of success. So we've compared how this scales. It's like n to the big N. So big N is to the n number of all possible bit strings to the 0.417. So this is interesting for a number of reasons. The error bars are very small in this plot, I might add, they're smaller than the depicted symbols, because that's actually better than what you get for Grover-like search. So gate model Grover search, you get a 1 over square root n is your scaling. You can build a Hamiltonian version of that, and it gives you the same scaling. And in fact, you can show for an unstructured problem, meaning you don't get any information other than whether your solution is the best solution or not. You're not told anything about how far off you are for the best solution. This 1 over root n is the best you could possibly do. So this tells us that our algorithm somehow is using the structure. Somehow the fact that this isn't an unstructured problem, but is a structured problem, is telling us what's going on. So you might ask, okay, how long have we actually run this quantum walk? Turns out here there's actually 2 curves on top of each other. You just can't see them because they lie literally exactly on top of each other. There's an infinite time average, which you can just calculate using some special mathematical tricks. They're in the paper if you want to know how they work, or I can explain them after. You average over a time proportional to the square root of the number of qubits. Now you might think, oh, this is square root of big N, number of bit string. No, this is square root of the number of qubits, square root of little n. This means the system sort of equilibrates quickly, because these are essentially no different. What this means, if you're thinking technically in terms of phase diagrams, is we're probably in the precursor of what's called a paramagnetic phase rather than a spin glass phase, because the properties of glasses, the fundamental property of them is that they equilibrate slowly. If you're, I won't really touch on that too much. Those who have a bit more of a condensed matter background, that might be interesting to. Those who not, don't worry about it. I talked about the effect of these correlations and that we know they're playing a role. So this is also interesting because any classical algorithm is using the fact that different solutions are correlated. Otherwise, you couldn't have a classical algorithm that could do better than random guessing. When you do a quantum algorithm, you gain a square root, but a classical algorithm, if you're doing an unstructured search, meaning you can't tell how good an answer is unless it's actually the best answer, it's pretty obvious. You just have to check them all or try it randomly and hope you get lucky. But if we do some of these unstructured problems, first off, we seem to recover the square root n, square root n type scaling, or at least scaling that's no better than square root n. But also, interestingly, this parameter gamma, this how much you're hopping relative to the amount of phase you're getting, for the unstructured problems does have to be finely tuned. That's what these plots are. This is SK, which is this problem I mentioned where we chose the parameters at random. Here, these full width half max don't really grow very much, or doesn't really shrink very much, but for random energy model, it does. This just shows that the width really does shrink. And so the point here is people are using these, often use these unstructured Grover-like search to say, this is how you're getting a quantum advantage, is you're doing this sort of unstructured search. You're using that somewhere in your algorithm. And if you're doing these continuous time things, you're still using it in some sneaky way. Fundamentally, something kind of different than that is going on here. The behaviors are all looking very different than unstructured search, which in this case is good because we don't want to have finely tuned parameters. Both because that's experimentally difficult and because if you don't know what the parameter is beforehand, if you can't calculate it by hand, then your algorithm's not actually useful if you don't have some way of getting that. So I've kept mentioning sort of unstructured Grover-like search. I can just talk about this sort of briefly in one slide, actually explicitly looking at that. So here you can have a problem Hamiltonian that's a single marked bit string. Basically, your Hamiltonian's just this. You've given one state a different energy. None of the energies of anything else change. This gives the same optimal speed up as, again, the gate model algorithm, but is exponentially sensitive to parameter setting, as I said before. Here, the algorithms that give you a speed up all have to succeed with order 1 probability. In fact, you can show, I don't talk about here, that guessing doesn't really work. You can show that you can interpolate between sort of adiabatic and quantum walk mechanisms, but this sort of rapid quench quantum annealing mechanism actually just doesn't work for unstructured search, and probably doesn't work for these other uncorrelated models. So I've kind of previewed everything I'm talking about here, but we've started to look at other unstructured models. You can look in the paper for what the details of these are. Basically, this green one, we just sort of scrambled. We kept the same energies, but we just scrambled which bit string they corresponded to. That removes all the structure. Random energy model, we just assign bit strings random energy. Assigning a complete graph where instead of flipping one bit, you flip half of the bits randomly. All of these things, you end up with a success probability that scales close to 1, but a runtime that scales to be exponentially long. So, and for the two structured problems, this REMGC is we just took random energy model and forced the energies to be structured. They sort of go down. Okay, so the quantum walk story was very interesting. It told us something important, that the structure of the problem is really playing a role in these continuous time searches or optimization algorithms. This is maybe unsurprising, but it is very interesting, and it's something that kind of should inform the thinking about stuff. Now that we've studied these quantum walks, these are fruitful for understanding computational mechanisms, but something I glossed over a bit is the scaling of these is not actually significantly better than known classical algorithms. There's an algorithm called branch and bound that can give me basically the scaling I showed before. So it's interesting for understanding the physics and the mechanisms behind how these work. It's not interesting as it's not, at least without doing something else, it's not that interesting as an actual algorithm. So how do we build better algorithms on top of this result? There'd be two options. One would be to add a rapid quench to dissipate some energy. This actually seems to work quite well. That's what I'm going to talk about next and is the subject of our new paper. Or you can use hybrid subroutines, where you use information you have either from a previous call or from a classical algorithm. And I'll talk about this. The point is you can actually have hybrid subroutines which are coherent and which are sort of compatible with what's going on here. But now let's think about, rather than having just a quantum walk, what happens if our Hamiltonians change in time? And specifically, what if these A and B constants, rather than just being fixed, notice now I've put a sort of B in front of the problem rather than just having a gamma here. That's just a different way of scaling the problem. I'll switch between those throughout the talk. But what you can show is actually here, if you have a monotonic schedule, what you can do is you can split your time evolution into little time slices and then say, okay, I'm going to consider an instantaneous change in my Hamiltonian, then a little quantum walk for a short period of time, then another instantaneous change, kind of like a stair step. And this ends up behaving like a continuous schedule. This is called trotterization. It's commonly used in simulation of quantum systems. You go through some math and you find actually that the steps in between, you're just scaling down what I've now called H drive rather than H hop. That's just the convention that's used more in quantum annealing rather than quantum walks. It's the same thing though. You scale this down, you're actually further pulling energy out of the system. And details can be found on this paper, which is our new one. But so this is interesting because it's a very general result. It extends a spin glass result, or this quantum walk result, that you always are doing better on average, to any quench which is monotonic, meaning you're always either decreasing the gamma or keeping it the same. You start in the ground state of your driver Hamiltonian, and there's a third criteria, which is more of a technical criteria that you don't need to worry about. And in all realistic cases, that one should be fine. But I put it up there just for completeness. What you can do, what is allowed for this result to hold, there's no limit on how fast the algorithm can run. Discontinuities in this gamma are okay. So with a quantum walk, you could think of that as a quantum anneal, where you start off with your transverse field very high, instantaneously change it to some intermediate value, and then at the end instantaneously turn it completely off and then measure. So discontinuities are okay. And finally, your driver Hamiltonian, I haven't said anything about it being diagonal and an orthogonal basis to the problem. In other words, this ground state can actually be biased. It can be biased towards certain states. It doesn't have to be an equal superposition. And I'll talk a bit later about how you might do that. So the point is, schedules like this, where you maybe sit around at some point for a while, do something like a quantum walk, instantaneously change very quickly, that's all fine. The thing you can't do is what's called, or the thing that would make this proof no longer hold, would be if you went and you actually increase this gamma again. So this is like the quantum of the reverse annealing feature on D-Wave devices. This wouldn't hold on D-Wave devices anyway, even for these kind of schedules, because those are open systems, and this is all for closed systems. But you can't have this kind of protocol. Or you can, but our proof doesn't hold. So let's think of an intuitive example. Let's think of the next most simple intuitive example beyond just a quantum walk, which is a two-stage quantum walk. So now what you do is you have this gamma parameter, which is how much you're fluctuating, how much you're hopping between the different bit strings, between the different states. And you start off by turning it at one value. In this example, we just picked 4. And then you let it go for a while, and then you change the value. And turns out you can plot the energy expectations. This is for a small problem, if I remember right. This is for like a 9-spin Sherrington-Kirkpatrick. It's in our paper. You can find the details there. But basically what happens is your initial quantum walk, you increase your success probability a bit. Your energy expectations kind of fluctuate. Your total energy expectation remains at 0. When you scale this hopping Hamiltonian down, at least the way we've defined the energy, your energy expectation decreases below 0. You have a discontinuity in the energy with respect to the driver Hamiltonian because you've reduced its strength. But then when you do this, more energy goes into this driver portion of the Hamiltonian, goes back into it. And that means your expectation with your problem Hamiltonian goes down further. And in this case, the success probability went up. One thing I will say is nothing about what I've said here guarantees that your success probability will increase. Numerically, we found it always, or at least typically it seems to. There are some cases where it decreases, but the vast majority of cases it does increase. But there's nothing theoretically saying it has to. There's no theoretical guarantee. Whereas there are theoretical guarantees that this has to be below 0 all the time, and that you're, on average, you do have to be better. So this is sort of the simplest intuitive example. just to sort of give you a feel, this is nice because rather than thinking about continuously changing, you have just this one discontinuous change to worry about. And it shows you what's happening continuously in a quench when you're changing this smoothly, which I'll talk about later. So the rapid quench result that I keep going on about, why is it important? Well, it's general, but it is a bit of a weak statement. Because all I'm saying is it's at least as good as measuring the initial state, which if you have an unbiased initial state, it's at least as good as random guessing. And so, okay, but it is actually important for a lot of reasons. One thing that it says is you don't have to worry about your dynamics being counterproductive. Your dynamics are never going to decrease the quality of your solution. So when you're designing protocols, when you're deciding how do I run my adiabatic or my annealing protocol, or what parameters do I pick for my quantum walk, you just maximize the dynamics. You don't need to worry about, are the dynamics going to help me? You know they're going to help you. That's what this theory says. You can also, as I already mentioned, use a bias search. And an important thing is this gives you a way of understanding dynamics very far from the adiabatic limit. And that kind of theory doesn't really exist. We have lots and lots of theory that exists in the adiabatic limit. There's not a lot of theory, though, if you say, well, what happens if I excite a lot of excited states? What happens if, rather than just the ground and first excited state, I have, hundreds or thousands of excited states excited? It's hard to say anything. And we're starting to get there. And this energetic perspective seems useful, which is the title of the paper that I keep referring to by the archive number, is an energetic perspective on quantum annealing through quantum walks. So let's talk about designing protocols to maximize dynamics. So the idea here is, okay, I've already justified that we really just want to care about how much dynamics we have, not about whether or not it's helping us, because we know it's helping us. So what we really want to do is we want to balance off two things against each other. We want to balance off the ability to transfer between these bit strings and jump between them. And so we've defined this quantity here that just sort of measures how much you're doing that. It's basically the off-diagonal element over the sum of the diagonal and off-diagonal elements in a two-state subspace. We call this transfer coefficient. This is, again, in the archive paper I gave a reference to a few slides ago. But you want to balance that against how much you're actually seeing these phases that are coming with each bit string. And so here we have defined what I've called the disequilibrium coefficient, which is how much you've broken the initial equilibrium. Because if you want to just maximize this transfer, well, what you do is you just don't turn your problem on at all. And you can see here I have a plot. This is shown in, this would be having a very high gamma. So this blue curve, you see this blue curve just keeps going up as I raise gamma. If I make gamma equal infinity, it'll go to 1. At the same time, you want to balance that off against still having some of the information of your problem, which can be defined just by rotating this into the diagonal basis of the problem rather than driver Hamiltonian, and doing the same thing. Here, at gamma equals 0, this is 1. You're getting lots of phase information about the problem. But if you just do that, you have all the information about how good a solution is, but you don't have any, your states aren't transferring between the different bit strings. So we argue, okay, well, what you really want to do is just maximize a quantity that's the product of these two. For JK are just a pair of bit strings. So a pair of bit strings connected by the driver, a pair of bit strings that are, in the case of transverse fieldizing, a single bit flip away. And what you can see here is this green curve, there's a finite value of this gamma coefficient where it's maximized. And so here now you have something you can really sink your teeth into for designing protocols, and sort of maximize this. So, okay, can you actually use this? Let's look at a simple 2-qubit quantum walk example. That should say 2-qubit. P100 is the average success probability for a time up to 100 or less than 100. Basically, this is doing the same averaging we talked about before. And what you can see is that peaks very near where the amount of our dynamics peaks, the level of our dynamics peaks. And that's maybe not so surprising when you think about it, because we've already argued that the dynamics are always beneficial. Now we're just saying, okay, what you really want to do is maximize your dynamics. This is a heuristic, so it isn't perfect, so you're not exactly on the peak, but you're pretty close. I mean, you're maybe doing, have a probability of success of sort of 57% rather than around 60%. It's not that different. So then you say, okay, well, that's a pretty artificial 2-qubit problem. What happens if you really think about these real sort of Sherrington-Kirkpatrick, these sort of optimization things that look like real optimization problems? For instance, the heuristic that I didn't talk about, and I referred to this New Journal of Physics paper for, what happens if we use this trick to find the optimal value of this parameter gamma rather than using the sort of fine-tuned heuristic we did there? Turns out the answer is it is almost the same. You can see this red and blue curve. It's slightly worse, but the scaling is barely worse at all. So the point is, this seems to work very well numerically. This seems to be a very effective way of choosing this gamma for quantum walks, and it's very general. So now you're given a problem. It can be any kind of problem, and you can actually just sample from the different solutions. Because you only need to consider two-state subspaces at a time, you can do this for very large problems. You don't need to be able to represent the whole problem numerically. So if you're given a large optimization problem and you're saying, I want to solve it with try quantum walk to solve it, and pretending you have a large machine that can do that, you can find the parameters just by classically sampling, by classically just pulling up 2 random bit strings that are 1 bit string apart, assuming you have transverse field, or that are connected by your driver Hamiltonian if you don't, and represent that as a 2-state subspace, calculate these quantities. That's all efficient, and you have some sampling error, and you can show that that's all efficient, and it all just kind of works, and will work for larger sizes than you can access, than you can fully simulate numerically. And so, okay, can this also be used for anything else? Well, one thing you can do with this is you can say, rather than a quantum walk, let's consider a quench, a quantum anneal, and try to design a schedule there. Well, if I want to spend more time where there's more dynamics, I have this dyne bar, which is just this quantity over JK averaged over the different pairs. And I can just change this S parameter, which is basically, it relates to the ratio of these two, defined in this way here. And I can use this to design a protocol for a specific instance. Here we used a random Sherrington-Kirkpatrick instance. And what we found is our success probability is better with a schedule picked in this way than with a linear schedule. Not by a huge amount, but this is also a very unstructured problem. If you had a problem with more structure, where maybe you had some constraints with one energy scale and the rest of your problem had a different energy scale, then you might see a bigger improvement. But the point is, this theoretical way of thinking about this this way of thinking about these problems in terms of you have dynamics. The dynamics are always helpful. You just want to maximize the amount of dynamics you see. It seems to work. It seems to be a valid, good theoretical tool. So let's go back to some numerical examples. Let's do a more complicated example. Let's do a numerical example where we actually have a continuously changing parameter. So here I'm going to think of still a quantum walk, but now what I call a pre-annealed quantum walk. I have a quantum walk, so I stop at some finite value of gamma, but rather than just instantaneously reducing gamma to get there, I, over some time scale, smoothly reduce it. This, by the way, is actually what you'd have in a realistic system. Oftentimes you can't change your controls instantaneously. For instance, in flux qubit systems, you can't. And what we have is we have these dotted lines are basically where it stops. The dashed and solid lines are A and B, the different A and B parameters in the Hamiltonian. In this case, A and B just happen to be the same at the end. That just the instance we picked that ended up happening. There's nothing deep or special about that. And you can see in this single example, the longer you pre-anneal, the better you do. This kind of makes sense. You're pulling out more energy by going slower. Again, if you're thinking about this in terms of condensed matter theory, you could say, oh, maybe I'm stopping in this paramagnetic regime to avoid the exponentially small gaps in the spin glass. Maybe that is. We haven't really analyzed that fully to really understand whether that's what's going on or not, but it could be a plausible explanation. So if we actually look at the scaling of these spin glass problems from this Callison paper, so this is results in our new paper, but we use the same set of problems from this new Journal of Physics paper. And you look at the success probability and how it scales. It scales down with size, but the longer you pre-anneal, that's what this T1 is, the more gentle the slope becomes. So the longer this initial ramping down is, the more gentle this scaling slope is. And you can calculate this kappa, which is basically how it scales with the number of qubits. And yeah, you can get that it scales down, and you can see you can go from this about 0.4, which is the result from this paper, to something that's 0.2 something. So this around 0.4 is around where the best classical algorithms are. You're getting significantly better than the best classical algorithms. If you fine tune it a bit more in this kind of busy plot, so these red and gold lines are the parameters we use there. But if you do some more fine-tuned parameters, exact details of what we did to do this aren't that important. You get even nicer scaling, sort of 1.5. This is compared to what I talked about, this green effective scaling for a state-of-the-art classical algorithm. This is something called branch and bound that I've included for comparison. This branch and bound is actually deterministic. It actually succeeds with probability 1 after a very small time. But I can take 1 over that time to convert something that looks like a probability. And the scaling there is 2 to the minus 37. So I've about half that with these really good ones. And even the sort of not that optimally chosen ones are still doing significantly better. This is cool. The pre-annealed quantum walk seems to beat the classical state of the art. There's all the caveats of these are finite size simulations. Maybe something changes when you get to larger sizes. However, if you look on these log linear plot, these are very straight lines. It's looking like we're kind of are in the thermodynamic limit, and we kind of aren't going to see any anything bad happening out here that will ruin the scaling. But technically, we don't know that it doesn't. Scaling exponent less than half of the state-of-the-art classical. Those results are actually unpublished, the ones that are the very best ones. And the one other point is this paper here, people have done a quantum version of this branch and bound algorithm. And here our best scaling, when we really sort of choose the best parameters, is actually pretty comparable with theirs. Ours is 0.145, theirs is 0.186. I call that comparable rather than saying ours is better because there are some error bars on there. But the point is, that's a very tricky hybrid algorithm. What I mean by hybrid algorithm is it's using classical tricks on top of quantum. Whereas what we've done here is just pre-annealing. It's just a quantum walk where you've annealed to start out with to remove some energy. And so, yeah, there may be room to improve this even more. We'd still have to make sure that our choosing the parameters to get this scaling isn't cheating. That's part of why it hasn't been published yet. But the point is, this is all looking very promising. These sort of rapid quenchy algorithms, the scaling on the sizes you can simulate, it looks pretty good. It looks nice. Because that's sort of the end of one part of the talk, are there any questions anyone has before I move on to the next part?
There is actually.
There is, okay.
Yeah.
Because all
interrupting people.
Okay. Let's see. I can possibly. Okay. I can't. Okay. Yeah. Let me just. So let's look. Do we? Where are, or do you want to read some of them out, or where are they here in the chat? I see them. One unanswered question. So the question here is, what is the relation between quantum random walks on graphs and discrete graph Laplacian, which goes to a continuous Laplacian in a classical limit? Okay, that's an interesting question. So what we're looking at here is quantum walks on a very specific kind of graph. So you usually might not think of these as being on a graph because you're thinking, okay, there's just a transverse field. But if you actually were to write the solutions out, like the potential solutions, the bit strings, and look at the edges that connect them, look at the, let me just go back into the talk. Look at these sort of edges that connect the different states, you end up with a hypercube. And so here we're looking at continuous time rather than continuous space. As you increase the number of qubits, the dimensions this hypercube lives in increases, and that exponentially increases the number of bit strings because each time you add a dimension, it doubles. This is different from sort of a continuum spatial limit where you have terms that, or where you have sort of quantum walk on a graph where the Laplacian can be viewed as becoming continuous. There are some sort of interesting things that go on there, but I don't think there's a limit in which this hypercube graph sort of becomes continuum. We haven't really looked at how sort of continuous space, maybe discrete time quantum walks, might relate to continuous time, discrete space. In this case, it's kind of an encoded space. If you could just build this whole hypercube, you could just find your solution by looking at it. You can't. What you actually have is you just have the qubits physically, and then it creates this sort of abstract hypercube, which is the graph you're walking on, by encoding it. Yeah, so if there's a relationship there, I'm not really sure what it is. That could be interesting to look at, honestly. One thing that is worth pointing out here, though, is a lot of what makes these techniques powerful, at least for computation, is this encoding, is the fact that we don't have to actually build the entire graph. Because if you can build the entire graph while you're building it, you can just check the solutions. In this case, the graph's encoded, so you just build the interactions between the qubits, and you get this graph as sort of an abstraction, as sort of an encoded abstraction from it. That being said, computation isn't the only thing you'd use these machines for. If you're using it for simulation, all of a sudden, a graph that's continuous in space might be actually what's much more interesting, and you don't really maybe necessarily care about this encoding because you're not looking for a classical solution. You're looking for how something quantum behaves. So I wish I had a better answer for how these related, but the thing I will say is I think that's an interesting question, and I think it could be worth looking into how these might relate. So I think that's that was the only question I saw on the
yes, that was
Yep. Okay, cool. Well, so now I think I'll move on to the next part of the talk. So this sort of nicely previews what the next part of the talk is. So right now I'm talking about, okay, these techniques, they're interesting, but they're not hybrid techniques. Maybe you could make them better by also using some classical tricks. So by hybrid, I mean hybrid quantum classical. Hybrid can mean other things in other settings, but that's what I mean in this context. So let's think about that and think about how hybrid quantum classical techniques might interact with this. So hybrid subroutines in continuous time. Let's quickly review what there are. I just have this cartoon to sort of motivate the idea here, or one way of motivating the idea here is that in the case of quantum annealing, generally tunneling through broad barriers is thought to be hard quantum mechanically. Your gap shrinks exponentially, so your time to tunnel is small, becomes long. But in rough regions of the landscape, you can tunnel pretty easily classically. But finding sort of your way around something fairly smooth is fairly easy classically. So perhaps you could use a classical algorithm to get here and then win by being quantum afterwards. So there are known techniques. There's this experimentally implemented reverse annealing technique where there's a paper sort of talking about how you might do it. It's since been implemented. But this relies on the dissipation that's in these D-Wave devices. So the fact that these devices rely on a lot of dissipation doesn't necessarily mean they're not powerful, interesting devices, because they are. It's just thinking about them like they're running closed system algorithm doesn't really work. In particular, this algorithm wouldn't actually work at all in a closed system. It actually relies on the dissipation to work. So if we're talking about combining our result earlier with some hybrid algorithms, that technique's not going to fly for what we're doing. There's this technique by Perdomo Ortiz et al. That actually involves 3 separate Hamiltonians, but it involves some of this sort of going back, things where you turn some of the Hamiltonian terms up. So it's not compatible with our proof either. But originally introduced in this paper in Chinese physics letters, and then later examined by Tobias Grass in a physical review letters paper. I didn't have the date for the Chinese physics letter one. This is 2011, I believe. They've looked at what this just involves, instead of having transverse fields, you make them not exactly transverse. And remember back quite a few slides ago now, where I said, oh, one of the things you don't need for this proof in our paper is you don't need the driver Hamiltonian to be an orthogonal basis to your problem Hamiltonian. Well, the way this biases the Hamiltonian is just by having a field that's not exactly transverse. Your ground state, because they're decoupled, effectively decoupled spins, are your driver. You just rotate your ground state along with them, so the ground state's still easy to prepare. And this is compatible with our proof. So this is the technique you'd want to focus on, at least for closed system dynamics, where you want to actually show you can reduce the energy. So before I get to this, let me just back up and talk a bit about the one you can experimentally play with, which is this reverse annealing one, which is actually implemented on a device. So how does this work? How does this sort of bias search actually work? Well, you can imagine I can build a spin Hamiltonian. I can get into the details of how this is actually built if people are interested. But you can build this spin Hamiltonian where the effective energy landscape has a broad false minimum. So if you just normally annealed, you'd end up here. You'd have a very thin, very narrow gap at some point where you could tunnel between these two. But unless you go very, very slow, you end up here. You start here, and then you have some true minimum that's sort of narrow, and there are other states you could end up in just by accident. And so you start here, and what happens is S prime effectively controls, the smaller it is, the broader your search is. So you can see if you don't search very much, you just start in your start state, or you just stay in your start state. You stay in the state you initialized. Eventually, you can kind of tunnel here. There's a point where you just sort of stay here. Ignore this magenta line. It's not that important. And then you can end up sort of in this true minimum. So you can imagine if you were actually trying to solve a problem, this is really good, because if you biased to this good guess, you can find it with high probability. But if you search too broadly, you just get stuck in this false minimum, the same as if you did traditional quantum annealing. So this is just sort of a proof of principle experiment. These are experimental data. You end up in other states at some points too. Mostly it seems when you're tunneling between these, you can sort of get stuck halfway. So that's sort of the concept of this bias search, and actually demonstrated with a real physical experiment. People have used these in algorithms. Sorry, this is kind of a busy slide. And they've had some moderate success. You can search locally around classical solutions. You can do iterative search. You can use this in certain kinds of quantum simulation. And people have used this in sort of genetic algorithms where you can find a global optimum quickly, where other methods are struggling. There's some theoretical discussion on it. This is actually mostly work by other people, I should add. But the point is, there are some early proof of principle algorithms. Most of them are as simple, with the exception of this, which is a bit more complicated because it's a genetic algorithm. And you're still seeing fairly good advantages from this. So it looks like being hybrid quantum classical for optimization is a good idea. So now that we've sort of motivated that, let's go back to doing numerical experiments. And let's look at some of our work with this biased driver Hamiltonian that was developed by this two papers. Someone by the name of Duan, who wrote this Chinese physics letter paper, and Tobias Grass, who wrote this other paper. And so we formulated ours slightly differently, but the basic idea is you start in a ground state where, like I said before, you have individual spins. You rotate the spin. This G is what your guess is, a guess bit string, so you rotate toward that guess. And you bias toward a classical bit string. You can think of it in a cartoon as you have these fields that aren't exactly transverse. You include some interaction. This is all unpublished work. But you look at this and you say, all right, what happens if I consider a guess where each bit has an independent, or each qubit, each bit of my guess has an independent probability P of being wrong? This probably isn't super realistic for what you get out of a classical algorithm, but it's simple and it allows you to look at stuff. And so then you can look at how good does a guess need to be before biasing parameterized by this theta. So basically, this color axis is success probability. This blue line is where the optimal angle to bias is. And this is the probability for each bit to be wrong. And what you see is right around where your guess is just a little bit better than completely random, it's actually a good idea to start biasing. And when you're around sort of only 40% likely to be wrong, so 60% likely to be right, biasing quite a lot is actually the optimal strategy. So this is for an 8-qubit max 2 set problem. I should add max 2 satisfiability. That probably doesn't matter that much. And this is preliminary work by Lauren Shunita, my PhD student. And so yeah, we're still looking at these sort of bias drivers. But the point is, there's these sort of 3 techniques that are known for doing these hybrid algorithms. And one thing our work has shown is it's shown that one of these 3 kind of stands out in that you can have an actual proof that it will always help. And where you can use this concept of, okay, all I really want to do is maximize the dynamics, and it works with that one. So that's sort of just a whirlwind tour over this. We still need to do quite a lot on this bias driver stuff. It's pretty preliminary, but it's given some interesting results. So next, I'm going to quickly talk about what another issue with applied quantum computing is, and one that tends to be a bit overlooked. So far, I've just talked about how you might solve problems in quantum computing. I've said, okay, we have a problem. We'll model it as a Sherrington-Kirkpatrick or a maximum 2 satisfiability, mostly Sherrington-Kirkpatrick, except for this last slide. But we don't really care that much about it, about the details of it. But turns out, if you want to actually use quantum computing, what problem you're trying to solve matters a lot. And this is sort of not as much a technical subject, but it is one that's worth, well, not technical in the sort of mathematical sense. It is still technical, but it is something that's worth talking about. So I have a few slides on that I'll discuss about this. Let's pretend that we have an arbitrarily large perfect quantum computer. If we have that, there are many algorithms and mappings, and we don't really need to pick them carefully because we have all the resources we want. But in the real world, what you have is you have machines that are slowly growing and improving. They're exciting, but they're actually very limited still. And so you don't want to just, pull one of the many algorithms people have worked out off the shelf and say, okay, we'll just do this for this problem, and we know it'll give us some huge advantage because it's been proven. You go, okay, well, we have to think about how our real physical hardware and how it's limited. And even picking the right problems to solve are non-trivial. It needs inputs from end users. So I've hired a PDRA, a postdoc, with a non-quantum computing background to help with this. And I've been working with some startups on this. And so if you think about this, you think about what makes a good sort of early use case. So by early, I mean on sort of NISQ type machines. So early quantum computers may be very powerful, but the thing to remember is they'll be relatively expensive. So you want high value problems, and they need to be hard classically. Otherwise, why bother with it? Because otherwise you'll just use a classical technique. They're also likely to be quite small. So what you want is at least your sub problem should have low throughput. It should take it should be relatively small. You could maybe be doing some machine learning with a very large data set, but solving a hard sub problem with that could be fine. But you're definitely going to want to be looking for problems that are small, or sub-problems that are small. The thing that actually goes to your quantum computer should be relatively few qubits. And NP hard optimization problems, which I've been talking about in this talk, are a good example of that. Simulation of electrons are another one. There are others as well. But then if you're thinking of how to make it the best, you want everything on the previous slide, plus you want to think about how to map it, right size and shape to map to an existing machine, or to special purpose which could be built. This is something people often don't talk about, is the idea that you could actually build an ASIC quantum computer, a quantum computer where you've actually designed your hardware graph around a specific use case. So you need hardware and problem mapping expertise about this. You need structures of interesting problem needs to be understood. So you need experts in the application domains of this. And you need these hybrid quantum classical techniques I've talked about, which requires quantum and domain expertise. So the point here that I'm really trying to make is this is fundamentally a multidisciplinary effort. We can't just go and sort of sit in the corner as quantum computing experts going, all right, well, we're just so brilliant, we'll just sort of, write out a bunch of stuff on our whiteboard and that'll solve the world's problems, and we don't need to talk to the people who've already been working on these problems for 30 years. We'll just come in on our white horse and do everything. That's not going to fly. You really need to be working multidisciplinarily sort of together. One thing that's quickly worth talking about is also that there's all kinds of cool things going on with quantum inspired, with algorithms that are inspired by how quantum computers solve problems. For instance, at Fujitsu and Hitachi, those will have slightly different limitations. In particular, you don't need to restrict yourself to such small ones. I don't need to really be probably telling this audience this, but you still are probably going to want to do the genuinely quantum algorithms because there are quantum advantages, for instance, in unstructured search. But the point is, these should really be treated as synergistic. You should think, okay, quantum inspired is kind of how we'd win today. Full hybrid quantum classical is what you might do in the near future, or maybe less near future, depending how optimistic you are. And then you say, okay, well, then the next thing you'd expect is you just do everything on quantum. Well, why would you do that? Sub operations like adding numbers, you don't really need quantum for. So you probably never actually do that, because what's the point? But just, I've probably talked enough on this. One thing I will point out is it's important to actually think about methodologies for developing these use cases and for asking questions about what are the best problems to put on quantum computers. And so here I've developed some with some people from the company is actually changing its name, but it was until recently known as Applied Qubit, looking at, okay, how do you come up with a standardized methodology for looking at use cases for quantum computing? And so we came up with sort of a flow chart. The idea here is very much not to come in and say, we know best, we know what you need to do with this, but really to start the conversation for people to say, well, I think this constraint's really important. I think this is a question you should be asking for finding the best use cases. We would really like people to come in and say, you know, actually, we don't think this part of your flow chart is right. Because we're not trying to have the end all and be all here. We're trying to start what is an important conversation around quantum computing, which is, what are you going to use these things for when they start becoming useful? And how are you going to figure out what to use them for? And if you don't have a structured, organized way of doing it, then everyone will just pick their pet problem, focus on what all the good things are about it, sort of ignore the negative, shove them off in the corner and go, that'll be fine. And you don't really end up with any kind of fair comparison. What's much better is to come up with a really rigorous, established methodology of saying, let's ask these questions. If a use case, say, requires a lot of data to go through, maybe you say, you know what, let's do quantum inspired for now. And maybe when the technology catches up, this would be a good use case for quantum computing, but not right away. Is the value per instance high enough? And if not, is there a way to make the solution central? Another important question. You know, are you going to have to develop entirely new techniques to solve this problem? If so, is it worth developing those techniques? So with that, I think I'll conclude. Take-home messages, at least from the sort of technical parts of the talk. Unless P equals NP, all algorithms will either have exponentially low success probability, exponential single runtime, or potentially you could have a really bad one that has both. Nothing prevents that. You only need to remain coherent, though, for a single run. So it's less demanding for hardware. You actually probably need lower precision, which is something that we talked about earlier in the talk. And this is less psychologically satisfying to do these sort of mini rapid quenches, but there don't seem to be other real drawbacks. And so this is already what people do experimentally, is mini rapid quenches, because you just can't stay coherent for very long. So we as theorists, that's how we should be thinking about these as well, is thinking about these rapid quenches. And it's not as psychologically satisfying. You don't have all the tools, but it's what's more realistic to what's going on. Back to the very beginning spin glass part of the talk. One important thing is these correlations in these energy landscapes are playing an important role. And what's really important there is this works better than simple search. What I mean by simple search is unstructured search, is a case where you just only know if your solution's right or wrong. You don't know you don't know how close it is. You don't know how good a bit string is at solving your problem, other than either it's completely right or completely wrong. And our quantum walk algorithms our rapid quenches, seem to behave entirely differently from this unstructured search. And it suggests that maybe that's a very nice theoretical model, but maybe it's not really the way to think about a lot of real computation. Is not to think about that doing the work. It's to think something more complicated is going on, and it's using the structure of the problem in some complicated way. There's something interesting going there. This pre-annealing technique can give us competitive performance with the state of the art, and really starting to think of how to put this together with hybrid techniques seems like it would be worthwhile. We're working on that, but it takes time, and yeah, sort of some thinking about it. So with that being said, I think that's that's the talk. I'm happy to answer questions. Yeah.
Fantastic. Thank you so much. It's been very insightful. I can hear echo from my end. Do you guys hear anything, or maybe you can confirm that with me? Can you hear me properly?
I can hear you.
Okay, cool. Yeah. Does anyone from the audience have a question? In particular, I was asking the students to feel free to ask any career-oriented questions. If there isn't one, I myself ask you, what would you recommend someone just starting up, a graduate going into the field? What did you learn that you kind of wish you knew before? Any surprise?
So what did I learn that I wish I'd known sort of from the beginning? Is that the question?
Yeah.
Yeah. That's a good question. Okay, there are many good answers to this question. Let me try to think of the best one. I think one thing that I sort of wish I'd known is it feels like, especially when you're just starting out, like the sort of prettiest, more established people, the very established people kind of have all the answers and they know everything. The truth is, a lot of times with research, they're stumbling around in the dark just as much as a grad student or postdoc or something is. You're just not seeing it as much. And so I think sort of realizing that a lot of the research is about just trying to figure out how to phrase your own questions that you're asking, and kind of the importance of starting to come up with your own sort of independent research directions and starting to think of that early on. I would say also the importance of thinking about research projects strategically. In other words, not just thinking about this, what if this project works? This is great. We'll write the best paper ever, and it'll be on the cover of, every major journal, whatever. But what happens if things don't go the way I planned? And how do I still get a good paper? How do I design something so that I can still write a paper where if everything just, if I think I have a really clever idea, but nature doesn't quite agree with that. Nature, by which I mean, actual nature, not the journal, doesn't agree with that. And, how do I formulate questions where I can say something interesting even if I'm a bit surprised, I think is also kind of important. Yeah, and yeah.
A follow up on that, actually.
Yep.
About, you talk about independence and these things, how the current academia, the way the things, this sort of type of a peer review driven thing, how's that pressure and these things, how's that kind of in terms of encouraging, young, especially young researchers to pursue original thinking?
So there's always sort of tension between a lot of these things. And I think pursuing sort of original thinking is important. One thing that I should have actually also mentioned in the previous question is how long it takes something you've done to actually have an impact. Like, it's very easy as a grad student or, sort of early postdoc or whatever, to very early on say, okay, I put this paper out. It hasn't really gotten a lot of citations. People don't really seem that interested. It's very easy to get discouraged, but actually for a paper to really start to see its whole impact, it takes a very long time. People have to sort of see it and get interested in the ideas and realize it. Unfortunately, the way academia works isn't so compatible with this. I've heard some of my more senior colleagues say, okay, for a paper to really have its impact, it takes maybe 10 years. Well, what if you've only been a researcher for 5 years? None of your papers have really realized their full impact. And I mean, in some ways, there aren't necessarily good answers there. I mean, it's unfortunately, the system around academia can be quite a, I would say, brutal system, and I would say unnecessarily so, if I'm being honest. I would say just try to do something interesting, try to build a sort of good group and really come up with good things. Independence itself actually can kind of be a double-edged sword, because if you've gone and you've done something very unique, and I've actually had issues with this myself, because I don't actually have a permanent position now. My fellowship expires in June of 2021, and after that, well, hopefully I find something else. A lot of this, how it can be a double-edged sword is, if you're doing something very unique and you're looking for a permanent position, that can come back as, well, you don't really fit with what our group is doing because you've gone and done kind of your own thing. And, it's, that can be good for grant funding. That can be nice for, but it can also hurt you in some other ways. And, generally, what I tend to do is try to do good science and try to fit the career stuff around that as best I can, and realize there aren't necessarily always good answers here, and try to not take things personally. Try to realize, like, this really isn't a great system. If someone's telling you it is, they're probably lying to you a bit. And just you know, saying it, accepting that a bit, and not being too harsh on yourself if things don't work out the way, you know, sometimes don't work out the way you hope.
That's how life is, right? So
that's how life is. Yeah. Yeah.
And going back to the industry, since there is no other question, I will ask your crystal ball, in particular in terms of quantum annealing, for instance, because a lot of people, when I talk to them, sometimes the skepticism and these things, like, do you feel that the quantum annealing is being overlooked? The follow-up question about that is, at what point, what does the quantum annealers need to achieve in order to be looked at a more, I would say, at a more ambitious level, if you will?
So, first off, I think actually skepticism is in general very healthy. And I think actually the level of skepticism people have has actually probably been overall healthy for quantum annealing as a field. It keeps you a bit more honest. It kind of means you have to ask hard questions. I do kind of think there probably should be a bit more interest in continuous time. I think maybe the balance in what people are investing in should maybe be put a little more toward annealing type, continuous time type architectures, because I think there is a lot of promise there. There are, of course, limitations, just like there are with gate model. A lot of these limitations are actually the sort of graph structure you can realize. How to map a problem to something with very limited interactions can actually be quite challenging, and can give you a lot of overheads. I mean, theoretically, you know how to do it, but if you're talking a real physical system, things like minor embedding, the overheads from that can really kill you. So having better, more connected graphs will probably help. More control, bringing down noise, I think, is also very important. Also, now that I think a very positive thing is people are now thinking of this in a much more algorithmic way, rather than just thinking about quantum annealing as a black box that you just sort of turn the crank and it either gives you a good solution or it doesn't. And if it does, you celebrate, and if it doesn't, you just say it doesn't work. And I think thinking about these as sort of subroutines and as, okay, we have something that's going to be good in some ways and going to be bad in others. How can we potentially use this for something? So trying to do the crystal ball thing and predict when something might actually move to the sort of next level, that's always so hard to say. I tend to be a bit optimistic and say something fairly niche, seeing some kind of advantage maybe in 5 years-ish, or sometime within 5 years. That may be too optimistic, though. Certainly, I think being very widespread would take much longer. But then again, you only really need one nice niche application for things to really take off. There does seem in both annealing and gate model, there does seem to be steady improvement. And I do kind of think a lot of, at least on the theoretical side, a lot of the work in a lot of the work can be synergistic, especially a lot of the continuous time work. You can always use a gate model machine to simulate a continuous time machine. So while I tend to actually find a lot of promise in natively doing the continuous time, one other reason I really like this continuous time stuff is if someone says, well, let's take the hypothetical where gate model machine wins, where gate model machines, well, win, that's maybe thinking too adversarially, but where gate model machines advance very quickly. Okay, well, the best sort of NISCI way we know of solving optimization problems is doing things that look a lot like simulating Hamiltonians. So if I've understood optimization problems in terms of Hamiltonians, or understood quantum simulation in terms of Hamiltonians, well, that's actually going to be very useful in a gate model setting. And so, then I'd just be very happy that the gate model machines have done so well. So yeah, that's hopefully helpful.
That's great, and we won't hold you to the answers you gave about this.
Yeah. No, that's a complete guess. So it could be completely wrong.
Yeah, we have a question just popping up. I'm not sure whether this is. What about mentoring some enthusiastic students about QC? Was that directed to me, because we are running a program called formalism, which is about a mathematical formalism of mechanics. This is a general.
There seems to be some sound issues, so I'm not
Walid,
sure.
you are with us?
Heard everything. What?
Can you hear me?
I can now, but the sound sort of cut out a bit.
Yeah, no, I was just saying, I'm not sure whether this is directed to me because of the course that we will be offering on the mathematical formalism of quantum mechanics. Or this is a question to you, whether you are interested in mentoring students about QC.
I mean, in principle, I am. We do always have some summer interns in our group. That is how we sort of tend to do this, is by hiring, by finding funding to fund interns. We don't do unpaid internships because that just seems a bit unfair. But for instance, Matthew Walsh here was actually an undergraduate intern. Let's see, I think Max Fenstenstein actually also was. That's a bit too far. So we do sometimes sort of supervise projects with undergraduates. Usually we do this in sort of the summer thing. I also do have a graduate student in my group. So in terms of graduate students, definitely do that. Right now, with sort of the term coming up and not knowing what I'll be doing next summer, it's hard.
Well, I will be.
It's hard to know, but
thank you for a fireside chat with some of our students about career, where they can ask you more specifically career-oriented stuff.
Yeah. yeah, having some kind of career-oriented stuff would be fine. I'm like I said, I will point out I haven't necessarily like sort of won the whole academic career thing. I'm still on a temporary contract, so in some ways, you know, if your question is how do I get a permanent academic job, my answer might be, well, I don't know. If you have a good idea, tell me. But,
yeah. So this is done. There isn't any more question, but maybe I have one final one. I promise. This is the thing.
Of course.
In the context of this mathematical course that we are going to provide. In fact, I have a Q&A session on Friday with some of the guys on the audience here. So how does mathematics, the role of mathematics in research, maybe listening from you, a researcher in your field, will give them a bit more concrete thing, how important, getting mathematics is to getting into the field.
Yeah. So I think a lot of knowing the mathematics behind this is quite important. What I've found is important is being able to relate sort of the mathematics to the actual physical intuition. Different people have different sort of ways they think about things and solve problems. So this is going to be different for different people. But I know for me, being able to understand what the different pieces in the mathematics sort of physically or conceptually correspond to, which does mean knowing it at sort of understanding the background of it at a decent level, is what allows me to figure a lot of this stuff out, and sort of having a conceptual model that is built on the mathematics, but also has some sort of conceptual, okay, here's the mathematics, here's conceptually how I think about it, and then you can sort of, with that, sort of work on the different ideas of what could be happening, and then go back to the mathematics to check it to make sure that you haven't, like you've taken a conceptual leap that actually isn't good. Which the ones that do work out are the ones that get into presentations. The ones that don't go in the bin. But the thing to remember is there are those ones that don't, and there will be for everyone. You just don't hear about them in their talks because people aren't that interested in ideas that don't work, basically. But yeah, I'd say it's pretty important. I do think trying to lower the sort of barriers associated with mathematics is quite important. This is something actually that my graduate students working on, is a visual representation of gate model quantum computing. So actually at some point, getting you in touch with him might be a really good idea. He might actually be in the audience. I'm not sure. He said he might come.
Okay.
I'm not seeing Laura, if you're here, pop something into the chat real quick. I don't think he is. I think he probably wasn't.
We can have a follow-up of.
Wasn't actually able to make it,
yeah,
but
sounds good.
I can get you in touch. And yeah, I can see here someone asking if the slides will be posted, and I'm happy to do that.
Okay, cool.
I also do put all of my slides up on my webpage, which is in the description. So slides from previous talks, I haven't put the slides for this one up yet.
I will follow up with an email where I will send your online profiles, including your website, so people can go and find reference materials. Yeah. There isn't any more question. I know I already already taking a lot of your time today, and it was.
Oh, that's fine. It was enjoyable. It was a good.
Thank you so much for doing this.
Well, thank you. Thanks for having me.
Yeah. So for all who joined, thank you so much again for joining. Apologies for my joke about the cat, the Bob and Alice cat that was on the slide. So yeah, have a good day, and yeah, I'll see you next time. Nick, I will forward. Thank you so much. Okay, see you guys.
Bye.